Okay, good morning all. And today we are discussing on the new chapter from the module 3, compiler design system software concept, lexical analysis, right? So in the previous concept we have discussed on the phases of compiler. In that first phase is considered as an lexical analysis. Now in detail how the lexical phase is going to be works and what is the characteristic feature, functionality, and how it's going to be process the given input based on a particular application, right? Okay, just observe with the diagram is given in the first application slide. So as we know that basically when you are writing the program, we are basically concentrating on the compiler structure. Based on the C program, C compiler will process the data, and C++ program, C++ compiler will process the data, and Java compiler, Java, and so on. Like that, different compiler tools will be there in order to convert one language into machine understandable language. As you can see it in the interaction between lexer and parser, basically source program will be given as an lexical analyzer. The source program is acts as an input, and that will be passed to your lexical analyzer that will generate a token. So that generates a token. The token is accepted by the second phase of a compiler. The second phase is called it as an parser. And again, the whatever token that is going to be available, the tokens are going to be collected by parser by using a special method called get next token. So as you can see from the parser to lexical analyzer side, we are having a method that is a get next token. It is a method. It is keep on asking the lexical analyzer to generate tokens. For example, if you write a given program starting with your comment line followed by preprocessor directive, global variable declaration, main method, and again local variable and functionality, and each and every specific tokens are going to be generated is going to be collected by your parser, and till the termination the parser is going to be sending in get next method token to get the tokens from a lexical analyzer. And as you can see, so the symbol table is connected between both lexical analyzer and parser. Somewhere you will be defining two variables, four variables, sometime you will be initializing that, sometime without initializing you will be giving the value. Just if I consider Java application, constructors will be there, destructors will be there, multiple objects will be creating, inheritance concepts you are adding, inheritance with multi-level, multiple hierarchical will be there, and interface you have defined, abstract class will be defined. Like that, all the features are going to be placed in an integrated in terms of your symbol table. And once that lexical analyzer is keep on generating the token, the next phase is going to be collecting the token, and next again it is subsequently creates a parse tree for next semantic analysis part, right? So that gives that basic diagram how interaction between the lexical phase and parser phase, right? And lexical phase is a lexer and parsing phase is called it as parser. And symbol table is acts as a data structure where exactly it will store all the data, initialized variables, declared variables, and all the predefined values. Everything is stored in symbol table. To generate a tokens, it will link with the symbol table and keep on generating the tokens, and later when it is comes to computation, the symbol table is going to be referred. Sometime we'll be declaring the variable a is equal to 5, the value is going to be stored in a symbol table, and once the computation begins, it will check with the symbol table, and then it is going to be allocating a particular value, right? And next we move on to task of lexical analyzer, or we can call it as task of lexer. Basically, the task of lexer is always considered in terms of an lexemes, identification of lexemes. That is an fundamental and meaningful symbols or tokens is nothing but an lexemes, right? And stripping out commands. Whenever you are writing a program, starting with the commands, so all the commands will going to be removed by your lexical analyzer. The commands are not going to be processed by your lexical analyzer. So when you are compiling or any program, whatever commands will be taken, either single line comment or multi-line comment, that will not considered by your lexer, that will not going to be processed by your lexer. Very important. And lexical analyzer is removing that white spaces. It is going to be removing or deleting the white spaces, like you can consider blank space, white space, and slash and new line characters, slash t's, tabs. Everything is going to be removed by your lexer part. And correlating error message generated by a compiler. So again, that correlating error message generated by compiler is also going to be one of the choosable and identifiable task of your lexer. And it keep track of the line numbers in order to represent an error. Very importantly, the lexer is always keep track the line numbers in a program. So when you generate any program, so corresponding line numbers is going to be added. So as a user, you're not representing syntactically that line numbers of a program. We are just writing the program. Once the length of the program is incrementing, automatically the backend in the parallel process, the line numbers are also going to be handled. And to identify that particular error, once it comes to phase 3, semantic analysis, analysis part, then the line numbers are going to be identified based on the lexer. So that is one of the best part of your lexer. Right? If source program uses a macro preprocessor, the expansion of macros is also done by scanner. So again, when you're discussing on the first chapter based on the compilation part and the phase of the compiler, as I told, the lexical analysis, another name is also called as a scanner. So it is going to be scan the complete source program. It is going to be scan all the components involved in a program, right? So these are the basic tasks of a lexer, and these tasks are going to be compulsory and mandatory for any lexical process of an applications, right? Next, when you are combining the lexical process, again that lexical process is a combination of an two process, hence it is called it as a cascading nature of a process. What is that cascading nature of a process? So scanning is nothing but it is going to be take a source program, and again it is going to tokenize the data, and again it is going to be deleting the commands, removing the white space, whatever the task we are going to be identified, everything is going to be processed. But in the second process, cascading of the true process, in the second one, lexical analysis verify whether the portions of data or where exactly that scanner is going to be done, it generates an exact output or not. That is another task, very important. Means whether it is a valid token or not, that has to be identified, is one of the very important concept in the part of lexical part, right? So lexical analysis is going to be identified, and it is going to be process the data and the sequence whether it is valid or not, right? And what is the difference between lexer and parser? Means first phase is called lexical phase, and it is a lexer or scanner. Second phase is called syntax phase, it is called it as a scanner or parser. But what is the difference? What is the correlation, right? So in simple term, lexer is generated token, parser will generate an parsed. Lexer will take a source program as input, parser will take token as input, right? There's a basic difference we can see, that is a common difference that is going to be created between lexical analyzer and parser, and both will utilize a symbol table. So both will utilize a symbol table, that's a similarity. Dissimilarity means input is differ and processing and output is a differ, right? And again, both are very important for simplifying the compilation of design. So in order to simplify the compilation process, both the part is going to be very important. So to design any new compiler, user has to consider importance of both the phases. So then only user can create a new compiler. So simplicity of compiler design is one of the important consideration, and that depends on both the lexer as well as parser. And next, compiler efficiency is also improved. So by using this two part, the lexical part and scanner part and parser part, the compilation is going to be done efficiently. So uses a specialized techniques for lexical analysis called it as input buffering. So input buffering is a specialized technique that is used by your lexical analysis to enhance the efficiency, to enhance the effectiveness of your compiler, right? It's a specialized technique for lexical analysis part. So to analyze the tokens, generates the tokens and scan the complete program, and identifying the command lines and removing it, and striping off with any white spaces and any correlating errors, and checking with the line numbers the errors are going to be available, and any macro processor definition, macros are going to be defined, and any jump instruction that connected to macro, everything is going to be considered as an lexical analysis part. And next, to enhance the portability of a compiler, lexer versus parser plays an important role. So that's why both are going to be separate phases in a compilation, and role are going to be separate, but both the roles makes the compiler efficient and effective, and design the compiler is always going to be better if you choose the two different phases when you're designing and implementing a user-defined compiler. Next, we go on to definitions of what is tokens, what is patterns, and what is lexems, right? So token, when you are calling the term token, again it is nothing but how the tokens are going to be generated and how the tokens are going to be identified. But now we'll see how tokens are going to be defined. In terms of technically, the token is nothing but a pair of consisting token name and an optional attribute value, right? So when the tokens are represented, it is always having an pair of data. So one token name, and again it's an optional attribute value. So both will be there. So in the previous class we discussed on example for some expressions a is equal to b plus c. So a is a one token and it is having some specified attribute value. So sometimes the value will be there or value may not be there. And b is one token, value will be there or value may not be there. So while computation you'll be allocating the value, but initially it is having some attribute value that is an optional. So that's why it is called it as an token. So token is always a pair of values. One is a token name and corresponding attribute value. So what is token name defines? Token name is nothing but just a symbol. It is just a symbol representing a logical unit of a program. So smallest logical lexical part of a program is called it as a token, and we can call some examples in high level programming language called keyword as well as identifiers, right? Then again, what exactly that value? So values is nothing but allocated data. So value that is going to be processed, that is considered as a value, and the token names are the input symbols that is going to be parser is going to be processed. And when the token names will be there, it is having some input symbol. A is equal to b plus c, equal is a symbol and plus will be symbol, that is going to be processed by the parser. But there is no token will be generated for an operators. Tokens will be generated for a meaningful values, meaningful sequence of statements, of meaningful sequence of characters, right? That is nothing but tokens. And next we move on to pattern. Second definition. What is pattern? So when you're representing a regular expression in Unix and system applications, and when you're representing automata theory, the pattern plays an important role. So what pattern you are going to be searching, or we can call in algorithms pattern matching algorithms, pattern searching algorithms. So some patterns we are going to be searching. Some statement is given, we'll be looking for some specific pattern, right? Mathematically we'll be representing as a pattern, right? So in simple term, pattern is nothing but a description of some format, description of some form, where exactly that lexemes of token may is going to be processing the data, right? So in meta language term, pattern plays an important role. So regular expression, so when you're representing a regular expression, we'll be giving the patterns. When you're converting DFA to regular expression, we are giving a pattern. And when you're matching derivation of a leftmost derivation and rightmost derivation, we are giving a pattern. If you want to derive a string, we are giving a pattern. Based on that pattern, user is going to be identifying the string is valid or not. So pattern is a meaningful sequence of form of data, meaningful sequence form of data, that is a description, that gives a description, right? So if I take a token name as identifier, what is a pattern for identifier? How we can represent an identifier? If I take token name as a variable, what is a pattern? So variable name should not start with a special character. That is a pattern, right? So if I declare a data type declaration, so obviously the pattern data type followed by identifier, data type followed by variable name. So if I take a pattern of header file, obviously hash is going to be then include will be there, then angular brackets, then again followed by header file name, then followed by corresponding closing bracket. If I ask the token name as a package in Java, then pattern import keyword java.io.star semicolon, right? So pattern is nothing but it gives a meaningful sequence of characters, and again that is going to be matched based on the token name. So for a token name, if I take variable, I cannot write a pattern as a data type. If I take a pattern as an some variable declaration, then I cannot take token name as in void main, right? So both has to be matched, token name and corresponding pattern, right? And next we move on to lexemes. What is lexemes? Sequence of characters in a source program that matches the pattern of a token is identified by a lexer is an instance of that token. So very important, lexemes. So what characters or sequence of character that you are going to be matched, that has to be verified. If I take token name keyword and the pattern is I followed by F, and again it is specified within a square brace. So again it is an Unix and application programming concept. So again it is a meta characters. I am not specifying any range, just I am giving I as a single character, F as a single character. So if you want to make as a meaningful statement, so matching part, so I can easily call FI is obviously wrong syntax, because FI there is no syntax in C, C++ and Java. Obviously that syntax should be lexeme should be if. So that is a meaningful and matched pattern of a given token, right? So just look at with some examples how token and informal descriptions and how sample lexemes can be generated. So if I take a token if, the characters I and F will be there, and if I take else, the characters E, L, S, E will be there. And if I take comparison, different characters like less than, greater than, not equal to, everything will be there. If I take ID as a token, letter followed by letters and digits will be there. So you can take pi, score, anything, and you can take pi followed by 5 number, you can take score followed by 1, like particular token informal description of definition followed by sample lexemes. If I take number, numeric constant, that numeric constant we can again further describe it into decimal, floating point, again long integer, short integer, double, like the different sequence you can specify. So numeric constants will be there, that can be anything, right? And literal, enclosed within a double quotes, enclosed within a double quotes is nothing but a literal. So this will give the differences between what is token, what is a pattern, what is a sample lexemes, right? Next we move on to Another best task what we discussed in the first slide, that recovery options and identifying errors in a given program. So lexical errors. So as I told, lexical and parser doesn't have an error capability. So it will generate a tokens. If A greater than B, it will generate a token. Similarly, if I take A, if A less than nothing character or no character is entered, then again the lexical error is going to be identified. But again, it is not technically identify whether it is an error or not. So it doesn't have any type of capability, but minimum processing activity will be there for a lexical. Tokens is valid or not. They just identifies valid or not, but it doesn't generate an specific error in a given program, right? So just I'll consider panic mode recovery. So in case of any lexical process, how the recovery options will be done. Lexical errors, recovery options can be implemented. So deleting the successive character from the remaining input until lexical finds will know the token at the beginning of the input whether it is left out or not. So it is going to be deleting it. Deleting one character from remaining input, insert one missing character into remaining input, replacing a character by other, and transpose two adjacent character. Like that, it is going to be modifying it, right? As I told, it doesn't have complete error capability, but it is going to be do all different activities. So just it will delete one character and verify whether remaining input is valid, and by inserting a new character it will check whether it is valid, replacing a character and it will check, and again it is going to be transposing, then again it will be checked. So just look on with some simple example. If I take fi a less than b, so it will be replacing it firstly, and it is deleting it, and again it is going to be transposing it, and then it is going to be modified, then it is going to be identified. Okay, this is a valid syntax, right? And again check with the next int a comma, nothing is given. Next what it will do, it will take int a, then it will put a semicolon, or it will take int a comma b, then again it will add something, right? So based on this basic process, a lexical analysis is going to identify what are the different errors can be available, or it is going to be processed in a given program, right? It is a basic part of a program, but that doesn't have complete error checking capability. Even the scanner, it doesn't have any process. Parser is also doesn't have any. For the first two phases, it generates a tokens, it will generate a parse. But slight modifications in a given syntax is again identified as an recovery options. Again, it will be an option. As the name suggests, it is just an option how to recover by remodulating or rectifying the basic syntax. How lexical analysis will predict it whether that it is valid or not, right? And next we move on to very important concept called it as input buffering. So it is a technique, as I told, it is a technique for a lexical analysis. So it makes more efficient for a compilation part in the terms of lexical analysis. So input buffering is a lexical analysis technique, and again it is going to be improves the efficiency of compiler. It makes a better operation for a compiler, and it is going to be effectively approaches the compilation process, right? And just as I given in the first part, to speed up reading of the source program, input buffering is required. Efficiency wise it is going to be increased, and effectiveness wise it is going to be increased. And single buffer followed by one buffer technique. So two different names we can call. In exam they will be asking define input buffering and what all the techniques are available, right? So input buffering is an enhanced and efficient technique of a lexical analysis part to improve, to speed up the working of a compilation in terms of lexical analysis process, right? In that first method is nothing but single buffer or one buffering technique, right? As name suggests that in single buffer or one buffering technique, we use only single buffer to store process character from large number of characters of your source program. So for example, when you are having that given program, so that given program, if the lexem size, it is always checked with your buffer size. So given size is always comparing with your buffer size, right? So as you can see it in an example, a main override is that if main override is of if and lexem size is greater than buffer size. So if in case the word contain a 5 bytes, if word contain a 5 bytes, and if the capacity is of only 4 bytes, then again it is going to be contained with one word. It is going to be deleting within one word. So as an input buffer, so basically the word will consist of 5 bytes, but again that capacity will be 4 bytes. It will store the data, and again it is going to be reversing the data in a cyclic manner, right? So it reloads the data and removes and hold data. That is nothing but your single buffering technique. So what exactly single buffering technique? It doesn't hold complete data at a time. It will take the data and again it will delete or remove within hold data. That depends on the lexem size and the buffer size. If the buffer size is enough, lexems is fit and lexems is exactly matched, again there is no deletion of your whole data. That is very simplified example. Or else lexems are going to be meaningless, or lexems are going to be not processed or not understandable by next phases of your compiler. That is nothing but your single buffer and one buffer technique. That's a drawback. If lexeme size is going to be more and buffer size is less, or if buffer size is more, lexeme is occupiable, means again it is an easiest for an next phases of the compiler, or else it is difficult for next phase to identify and to process the data, right? And nextly, two buffering technique. So what is two buffering technique? So as the name suggests, in the previous one, in the single buffering technique, one buffering technique, only one buffers will be there, but there is less number of lexemes, means it is easy for process, but more number of lexemes, less than buffer size is less than compared to lexeme size, then again it is going to be very difficult. In two buffering technique, without sentinel, with sentinel, two different processes will be there. What is sentinel? So sentinel is just an way to approach where exactly that initiation and terminations will be identified. It is just given a identifier as an markers. So in simple term, we can call it as a marker. Sentinel acts as a markers. So whenever you are using the number of buffers, when you are using a more number of buffers, we need to identify when we need to begin and when we need to process and when we need to stop. So that is going to be identified. If the simplified word, single buffering technique is sufficient. But if your programs involved mathematical expressions, logical expression, array concept, indexing concept, then two buffering technique is needed. So we use the buffers that are alternatively reloaded. So alternatively, the buffers are going to be reloading it. So each buffer of same size will be there, and again it is depends on the capacity, block size of your memory, and again it is going to be read the systems and it will read the characters, and again it identifies with a specific data. So just take one simple example. Here I am considering the two buffers and b1 and b2. So where E is equal to mc square as an energy equation formula. So lexeme is going to be beginning, E is equal to, and again it will check with the lexeme begin at the C star, and again it is going to be identified with a forward reference. Forward reference will be there. So what is forward reference and backward reference? So when you're computing a mathematical equations or programming fault, either user can shift it from forward reference or user can again shift it towards backward reference, right? Both will be valid. So when you're computing E is equal to m star C star star 2, it depends on the value. It depends on how many number of values you are going to be computing mathematically, product. So mc square will be taken as mc into c. Two number of times we are multiplying the c. So that time where do we to begin with the lexeme and when we need to forward it, right? Each and everything is going to be identified in two buffering technique, and the special characters of end of marks will be identified, and end of the files will be identified, and end of the characters will be identified by using a sentinel. So it is very important part in terms of an lexical analysis. Next, what exactly two pointers? How to maintain the two pointers? So lexeme begin, as the name suggests, it is going to be marks the beginning of the current lexeme, and again it is going to be attempting to determine, it is going to be attempt to determine what content will be there, what equation will be there. That is going to be identified with a lexeme begin. Then what is forward reference represents? It is going to be scans ahead until a pattern match is found. Means sometimes we'll be taking an equation, by means as a programmer we'll be doing some logical mistakes, syntactical mistake, and that scanner has to be processing it. It will going to be forward. So E is equal to mc square, right? So just I'm writing the C, I'm not writing the C square. So that time until it find a pattern, it is going to be matching it. So that's why it is called as a forward reference, just to identify further whether it's a valid or not. It is going to be keep on tracking further. So hence it is called it as forward referencing. Hence forward referencing is required, and we need to check in two buffer without sentinels. So how to process the sentinels in the terms of an two buffer? So we need to advance the forward referencing. So sometimes if you taken any equation, so all the equations if simplified means it is identified, but if you take an complex expressions and complex equations, again it is going to be difficult to track the n number of sentinels. So using sentinels character at the end which is special or not, or whether it's going to be starting it or not, everything is going to be identified. Just check with the next example. So two buffers are there, and again you'll be taking E is equal to m in one buffer, and C star 2 you are taking it in another buffer, and finally EOF stands for end of the file. Means how it is going to be processed, how the sentinels are going to be takes it, so how the sentinels will be carried out, so how the special characters, how the initiation of the characters in an expression, termination, how to forward with the next equations, and when to end of the files process, all the features are going to be processed here, right? Next, go for look ahead code with a sentinel. So in terms of simplified switch case, we are just looking with an how the look ahead code is going to be works within a sentinels. So as we know with the switch syntax, so switch will be used as a keyword, then forward plus plus, so where exactly it is a pointer type, and again we are giving the case EOF. If the forward is at end of the buffer 1, the reload buffer 2. So once it reaches an end of buffer 1, then again it get inside and go with the reloading the buffer 2. Buffer 2 is going to be reloading it. And again you are going to be beginning with the buffer 2, then you are allocating to forward. Else if that is not a case, then forward is at end of the buffer 2. Assume you are at the end of the buffer 2. So reload the buffer 2 and check out. Still is there any pending characters or sequence of characters? Everything you have to identify. Then forward is equal to beginning of buffer 1. Again you will be shifting to buffer 1. Like that, the parallelly the schemes are going to be processed in and processing complete informations. Next, or else it is going to be end of the file, all the buffers are read or marks, then it is going to be stopped with an processing of switch cases. This is a very simplified examples how it is going to be works. And now we look with simplified definitions are required in a lexical, right? So again the alphabet, as we know alphabet is nothing but a finite set of symbols. So when you're representing automata theory, we are writing an alphabet 0 and 1. We are writing in special alphabets A, B, C. We are writing sequence of character. That is nothing but an alphabet. Then again, if I take a string, string is a frequent sequence of symbols. From it is going to be taken it from specific values, right? Sequence of characters will be there, that is taken as an alphabet. Then language is an countable set of strings over given input. So language is nothing but countable set of strings. So that is the difference between alphabet, string and language. Next, what is a prefix of string? So prefix is nothing but the string that is going to be beginning, that is called it as a prefix, and the string obtained by removing 0 or more symbol from end of the string, it is called it as an prefix, right? For example, if I take BAN, BAN, and epsilon or prefix of the given term BAN, ANE, right? Next we go for suffix of string. How to identify suffix of string? String obtained by removing 0 or more symbols from beginning of the string. It is not with the ending of the string, it is a beginning of the string. So it is an pre. So prefix followed by suffix. Again, prefix means end of the string, suffix means beginning of the string. What is substring? Substring is nothing but intermediate string. So deleting any prefix and suffix from a given string. So it is not like that initial or ending, it can be anything. Intermediate also you can take. Then what is proper prefix? Prefix which is not contain any data or equal to string, that is a proper exactly. So sometimes we'll be having an automata theory question. So represent an automata that contain exactly 2 A's, at least 2 A's, maximum 2 A's, at most 2 A's. Like some specific questions will be there when you're representing regular expression or automata theory. So by seeing the same definitions, we can easily represent the DFF based on the specific number of states. So how to take a data, how to input a data, how to take a given alphabet, and whether it's a valid or not. So everything can be identified based on the same definitions of your application programs, right? Next, what are the different operations on languages? When you're having pumping lemma theorem in automata theory, we are having some clean closure properties, regular language properties, union properties, concatenation properties, like the different rules you have studied. And same as your algorithmic approaches and automata theory compilations process, we'll be having De Morgan's law, commutative law, associative law, different laws you have studied, right? So based on that, what operations we can apply it on languages? Just we look on with operation, union operation, and concatenation operation, clean closure, positive closure. So what is union operation? So in mathematically, union is nothing but combination. If I'm having a 2 set, I'm combining this. And concatenation, just we are taking the 2 data and identifying whether it is invalid or not. Union followed by concatenation. Then clean closure. What is clean closure? It is a multiplication, a product of the given symbol, and again the symbol starts with I is equal to 0 to infinity, and the languages, that is L of I, and hence it is called it as L star. L star means 0 or many, and positive closure of L means 1 or many. So very important, 0 or many means it is always starts with I equal to 0, 1 or any means it starts with I equal to 1. That's a basic rule in an automata theory or Unix shell programming process. Next, what is regular definition? What is regular definition? Defines, right? So regular language we have studied, regular language we know, but what is regular definition? So regular definition is basically a definition. It is going to be define it for a particular language. So when we call that language as a regular, so the language is implemented and the language is deterministically equal, then I can call that language as an regular language, and that language can be identified by using pumping lemma theorem. The pumping lemma theorem will prove the language is regular or not. Now, what is regular definition? If I take some alphabet set as an input, then sequence of regular definitions will be represented in terms of an VTPS, right? Variable, terminal, production, symbol. So that will be commonly called it as a regular definition, right? So as you can see it in an example, D1 tends to R1, D2 tends to R2, Dn tends to Rn. So where each Di is a new symbol. So each Di is a new symbol, not in epsilon and other Di, and Ri is a regular expression. It will be some regular expressions will be there that will be identified as a given input, right? So just observe with the next C identifier example. If I take letter, what are the different ways you can represent? A letter tends to A, B, Z, and again uppercase combination and lowercase combination. If I consider a digit, then how we can represent regular definition? 0 to 1 followed by 9. If I take an ID, how we can represent letter followed by letter or digit followed by concatenation, or we can call it as star. So that is a sequence we can define it for C identifier. And similarly, if you want to represent unsigned numbers, how to write an unsigned numbers? So digit means we will representing positive numbers, and again digit means you can also have digit, digit, star, and optional fraction means dot followed by digit by epsilon. Optional exponent means E and followed by plus, minus, and E, digit followed by epsilon. Then number means digit will be there, optional fractions will be there, optional exponent will be there. So it is again basic representation. What exactly? Regular definition, right? Next we'll look at algebraic laws for regular expression. So how we can represent an algebraic expressions as an laws? As I told, different laws we have studied in an algorithmics, and again in terms of an logic designs, and again in terms of a microprocessor applications. Different losses are there, like commutative laws will be there, associative laws will be there, again distributive laws will be there, and again De Morgan's theorem, distributive theorem, everything will be there. So that can be represented. How we can represent it, right? So cumulative is a law, or associative is a law, distributive is a law that can be represented. It is an R followed by S is always same as an S and R. So that is considered of two entities values. And again associative, again it will be represented R ST, and again it is combination with RS then followed by T. Then concatenation, RST is one group, then RS followed by T is another group. And concatenation distributes with the help of specific law. Then again identity law for concatenation and guaranteed as a closure, then followed by idempotent law. Like the different laws can be represented for your regular expressions. Next, how to recognize the tokens, very important. So as a first phase of the compiler, tokens will be generated, and it is taken by the parser. The parser is again asked the tokens, and again parser is going to be generated parser. Now how to recognize the tokens, the first part. So if you're having the program, we'll be writing n numbers of syntax, n numbers of logics, right? And how to recognize that particular tokens, right? So statement, what is statement? Statement means if expression then followed by statement, or if expression then statement again statement, or nothing will be there. Means when you want to represent any expressions, how to recognize it as a token, everything will be represented in terms of an regular definition. That's why we in the previous concept we have discussed regular expression. And again we are seeing that where options, where number can be represented 0 to 9, 1 appearance followed by again 0 to 9 plus again question mark, that is an one or more appearance followed by your exponent values, right? Each and everything matching can be done, and identifies again uppercase to lowercase, and again it can contain one or more occurrence, and if followed by if, then followed by then, else followed by L, and relational operator. Here we are taking recognition of token for relational operator. So it's same thing, you can take it for unary, binary, ternary, anything you can take it. So that is relational operator can be less than, greater than, equal to, not equal to, everything. And white space you can represent it as WS, that is a blank, tab, or new line. This all be considered as a white space, right? Next, transition diagram will be look on. So how to represent a transition diagram? If I take a relational operator, and how to process that relational operator, right? If I take relational operator less than, how we can write a transition diagram? So that is a representation of a deterministic finite data. A start state will be there, intermediate state will be there, then again terminal state will be there, right? Less than means firstly it is accept a string less than equal to, then again less than other, again you can represent less than other, again it will be terminated, and again not equal to, equal to, then again greater than equal to, and greater than not equal to, greater than with other. So everything you can easily represent is as a transition diagram. So it is same as your deterministic finite diagram representation, but we are considering some expression, then how transition diagram can be represented, can be implemented. Next, just look with some syntactical pseudocode representation. So where you will be representing state 0 and token get the relational operator, and token returns the tokens to a new relational operator. Within the switch case, you'll be representing state. Case values are there. Within the case values, if condition, and it will return one value, else if, else if, and again case 1 it is going to be getting the character, case 2 it is going to be retract, and again case 3 retract, case 4 retract, case 5 is going to be getting the character, and so on. Different features are going to be added, right? And again case 6, case 7, case 8. So this is one simple example how to represent in terms of an switch cases. Now we'll take one simple example for identifiers. So as an identifiers, it will take letters, and A to Z is a lowercase, and again A to Z with an uppercase, then digit will be there 0 to 9, and ID will be represented, final values, letter followed by letter, then digit. Then in the DFA representation, or we can call it as a regular definition representations, we will be taking the start state 0, then again first it will take a letter, then within that it will take n number of values. That is a loop we have taken, a letter followed by digit, then other, then finally the final state will be your terminal state. So to get the token and identify whether it's invalid or not. So that can be represented in terms of a simple program. So it will take the data, identify data, and process the data. Next, again another example, just practice it, just to write it for unsigned numbers, again to represent it for keywords, and again to represent it for delimiter or word sphere. Just verify the syntax and identify and practice by yourself, and same thing, identify the different expressions and try to represent your own program logic and represent it in terms of an specification recognitions of your tokens, right? So again, this is your module 3 chapter 2, and these are all the questions. You can refer it for references, and these are the previous year question papers and all the concepts that are available, and just go through with an exact syllabus, verify with the question papers, and these are the sample papers that are asked in the previous year papers. And thank you for watching, and any doubts you just revert back in the YouTube channel. Next, again we'll discussing with the next upcoming concepts on module 4th and module 5th, that is of your compiler design process. And thank you for watching. Thank you.